স্যার আমাদের ইয়াতে ফাইনালে সিলেবাসে স্যার এমএলঅপস এর যে ফান্ডামেন্টালটা স্যার ইনক্লুডেড আছে স্যার। আমরা ওই কোর্সটা স্যার রিভিজিট করতে চেয়েছিলাম গতকালকে, আসলে রিভিজিট করতে পারছি না স্যার।
ওকে, ঠিক আছে তাহলে। অনেক আসসালাম। হ্যাঁ, কোর্স রিভিজিট করতে পারা যাচ্ছে না কারণ কোর্সের আমাদের হচ্ছে যেটা হচ্ছে টাইম ছিল 6 মান্থস। আমরা অলরেডি ওই লাইসেন্সটা এক্সপায়ার্ড হয়ে গেছে আর কি।
স্যার এটা প্রিপারেশন স্যার কিভাবে নিব স্যার, একটু রিভাইজ তো দরকার স্যার।
স্যার এটা কি ডিসকার্ড করা যায় ফাইনাল এক্সামের সিলেবাস থেকে এমএলঅপসটা?
ডিসকার্ড করতে চাচ্ছি না, কারণ হচ্ছে আমি চাচ্ছি আপনারা একটু পড়েন এটা, কারণ অনেকেই না পড়েই জমা দিচ্ছেন মনে হচ্ছে।
স্যার এটার কি কোনো মানে স্লাইড আছে স্যার? তাহলে সেই অনুযায়ী স্যার কিছু মানে
আচ্ছা, আমি
প্রোভাইড করতে
একটা কাজ করা যায়, সেটা হচ্ছে নতুন করে আবার লাইসেন্স আমি পাইছি, কিন্তু অন্য আরেকটা কোর্স থাকে, হ্যাঁ, একই কোর্স না, সেখান থেকে হয়তো ইনভাইটেশন পাঠাইতে পারি।
তাহলে স্যার একটু সুবিধা হয় আর কি স্যার, একটু রিভিজিট করলে সুবিধা হয়।
ঠিক আছে, তাহলে ওই আমাদের এর আগে একটা হচ্ছে ফর্ম দিছিলাম না, যে ফর্মটাতে হচ্ছে ডেটা ক্যাম ইনভাইটেশনের জন্য, ওই ফর্মে যারা যারা এন্ট্রি অলরেডি আছে তাদেরকে হয়তো আমি আবার পাঠাইতে পারি ইনভাইটেশন। এটা আর 6 মান্থসের জন্য পাওয়া যাবে আর কি। আবার যারা ওই ফর্মে নাই, যাদেরকে ম্যানুয়ালি পাঠাইছে, তাদেরকে ওই ফর্মেই হচ্ছে এন্ট্রি দিতে হবে আর কি, যাতে করে একবার পাঠাইতে পারি আমি। হ্যাঁ,
ওকে স্যার, থ্যাংক ইউ স্যার।
ওকে, থ্যাংক ইউ।
স্যার
হ্যাঁ বলেন।
স্যার আমাদের ফাইনালে কি এসভিএম থেকে ম্যাথ ইনক্লুডেড থাকবে? মানে আমাদের তো
থাকবে।
ক্লাসে কোনো এক্সাম্পল দেখানো হয়নি। ক্লাসে তো কোনো এক্সাম্পল দেখানো হয়নি স্যার।
এক্সাম্পল দেখানো হয়নি মানে কি?
মানে ফার্স্ট ক্লাসে হচ্ছে লাস্ট জাস্ট থিওরি গুলা দেখাইছিলেন, ওই ইকুয়েশন গুলা ডিরাইভ করেছিলেন, তারপরে বলেছিলেন যে ম্যাথ দেখাবেন।
সেকেন্ড
বাট
ক্লাস
সেকেন্ড ক্লাসে হচ্ছে ইয়ার থেকে শুরু করছিলেন, নন লিনিয়ার।
মানে আজকে যে প্রবলেমটা আমি সলভ করতে দিছি, এরকম কোনো প্রবলেম সলভিং দেইনি সেখানে ম্যাথে, এটা এরকম?
জি স্যার।
বাকি সবাই কি বলে, তাই কি?
জি স্যার, আমাদের
জি স্যার।
জি স্যার। স্যার বলেছিলেন প্রথম ক্লাসে বলেছিলেন যে মানে পরের দিন এক্সাম্পল থেকে শুরু করবেন, বাট পরের দিন আবার নন লিনিয়ারটা থেকে শুরু করা হয়েছিল।
আচ্ছা, ঠিক আছে, আমি তাহলে আপনাদের ওই যেটা রেকর্ড যেটা আছে, প্রবলেম সলভিং আছে, এরকম একটা রেকর্ড আপলোড করে দিব। জাস্ট রেকর্ডটা দেখলেই হবে যে নন লিনিয়ার বা লিনিয়ার যাই হোক, প্রবলেম সলভিংটা কিভাবে করে। ওকে
ওকে স্যার।
মানে ওই পার্টটা হয়তো জাস্ট টাইমের কারণে শেষ করিনি আমি, যেটাতে আছে শেষ করা ওরকম একটা ভিডিও আপলোড করবো আমি, মানে আমার এই ক্লাস আর কি।
ওকে স্যার, থ্যাংক ইউ স্যার।
স্যার সফট কনস্ট্রেন্ট থেকে কি স্যার আসতে পারে স্যার?
আসতে পারে তো
স্যার। ওই যে তিনটা নতুন ইকুয়েশন জাস্ট ডেরিভেটিভ থেকে বের করে নিতে হবে।
হ্যাঁ,
আচ্ছা আচ্ছা, ঠিক আছে স্যার, থ্যাংক ইউ স্যার।
ওকে, থ্যাংক ইউ।
স্যার সেই ক্ষেত্রে কি স্ল্যাক ভ্যালুগুলা দেওয়া থাকবে, যাই এর ভ্যালুগুলা?
হ্যাঁ, সলিউশন স্ল্যাক দিয়েও করা যায়, স্ল্যাক ছাড়াও করা যায়। হ্যাঁ, আমরা যদি সরাসরি হচ্ছে আমাদের হিঞ্জ লস ফাংশন যেটা আছে সেটা দিয়ে যদি করি, তাহলে তো আর স্ল্যাক লাগতেছে না সেখানে। হ্যাঁ, আর যদি এরকম হয় যে সেটা আমরা স্ল্যাক ভেরিয়েবল সহ করি, তাহলে স্ল্যাকের ভ্যালু দেয়া থাকবে।
হিন্টসটা স্যার মানে দেখানো হয়নি।
হিঞ্জ লস দেখানো হয় নাই?
না স্যার, ওটা জাস্ট এমনি মেনশন করেছিলেন, বাট ইন ডিটেলস কিছু দেখানো হয়নি।
আচ্ছা, ঠিক আছে, আমার স্লাইডে একটু দেখতে পারেন আপনারা যে কি আসছে সেখানে, কারণ হ্যাঁ অ্যাডাবুস্ট মিড টার্মে ছিল, আমি কোনো কোশ্চেন করিনি অ্যাডাবুস্ট থেকে মিড টার্মে। ওকে, তাহলে আমরা আজকের ক্লাস স্টার্ট করতে পারি মেবি। Hello, in our today's lecture, we want to discuss about at first the principal component analysis. The principal component analysis, this one is specifically known as our data dimensionality reduction approach. So data dimensionality reduction approach, it means if we have the more data dimensions, then usually maybe all those dimensions are not necessary. Okay, so that's why we want to reduce the data dimension, or we can say if we want to use the whole that is whole data, then it will take maybe huge computation. So we want to reduce the computation. Okay, so that's why we want to reduce the dimensions. Like maybe one of the data set you have, the dimension of the data is specifically we call it just the number of features. Okay, so let's say it has 10,000 features. 10,000 features. That means the dimension of the data here usually we consider 10,000. What PCA want to do, that means after applying PCA, we want to reduce the data dimension. Okay, maybe from 10,000 we want to reduce it to just only 10. So our data dimension will be, that is number of features will be like just only 10. So that means from 10,000 to just 10. But here actually this is not a feature selection method. Okay, not a feature selection method. In case of the feature selection, what usually we do, we reduce the features. Okay, or we eliminate some of the features. So the existing features we have, just reduce some of the features. Those are maybe not so important. Okay, but the PCA is also reducing the features, but it will transform the features, that means previous features, to a new dimensional space or new form. So that means it will transform the previous features into a new form. So that means in this form we will not recognize the same features. Like if we consider the age is here, the first feature. In our PCA, so this is the PCA. After applying the PCA, it will reduce the data dimension 10. The age is one of the feature, the name of the feature. In PCA we will say that this is PC1, principal component 1. We will not find age here. Okay, in this case we will not find the same features here. But in case of feature elimination, that means we can get the same feature age here. Okay, so that's why that means in case of the PCA we will transform those features, that means into a new form. Okay, so that's why after transformation, after converting to PCA, we will not get the same name like age, maybe the gender, maybe the date of birth or something, the age. Okay. So in principal component analysis, this is a statistical approach, style technique, finding the patterns in data of high dimensions. Okay, so that means this is the data of high dimension, 10,000 dimensions data. We need to find out something interesting here. Okay, specifically the variability. Okay, specifically the variability. We will try to find out the variability, and that will hold the in our first component, and then second component, third component, like this way. So it is to express the data in such a way so that it can highlight the similarities and differences. Okay, so that means the PCA, the first principal component, on that case it will hold the most variability, and then PC2, that is principal component 2, it will hold the variability less than the first one but greater than the third one, that is greater than the third one. Okay, so in this way, the PC1, it will hold the most variability. That means we will try to study the variability of our data, and then uh, we will transform those variability in principal components, and then the first principal component will hold the most variability, and then next one. Okay, to understand principal component analysis, we need to do some, we need to know some of the statistical and some of the mathematical, some of the mathematics and also statistics. Okay, like the mean, how to determine the mean. I think we know. That means if we have the variable x contains maybe lots of data, and then the mean usually we define, we determine by the number of data. So the summation of all those data divided by the number of instance or number of data points. So that is mean. So usually we represent the mean as the x bar if we consider x is our variable that holds our data. The standard deviation. So standard deviation and variance actually it determines the how the sparse our data is. So that means we need to find out the standard deviation at first. For from each and every data, we need to subtract the mean. So that means that from each and every data, we will subtract the mean. So how our data actually deviates from the mean. Okay, so deviates from the mean. So that is the deviation. So for each and every data point, we need to find out the difference, the actual data point minus the mean of our all the data, then a square of that, and we have to sum up for all data points. Then we have to divide it by n minus 1, and then a square root of that to keep it will give us the standard deviation. Okay, so here n minus 1, sometimes you will find out the denominator is n, not the n minus 1, specifically for this is called the sample standard deviation, and if we divide it by n, then this is called the population standard deviation. Okay, so population, that means for the population, if we consider the whole collected data, then usually that is called the population. So the population standard deviation is just we need to divide it by n, but in case of our sample standard deviation, we have to divide it by n minus 1. Similarly, we need to find out the variance, specifically the standard deviation. If we square the standard deviation, then we will get the variance. So instead of the square root, just we can say the sparseness, or you can say from each and every data to we have to subtract the mean, and the square of that and summation for all data points divided by n minus 1. So this will give us the variance. Okay, the variance actually it will define the variability of the data from the mean. So now the equation of the variance, you can see that actually we can see here is the summation of I equal 1 and up to n. So xi, if we consider the x is just a variable. Okay, a variable, it can be like age, or maybe you can say BMI or any of the feature. So X bar is the mean of our data point. So this one and a square of it. Okay, instead of a square you can write this one as xi minus of x bar. Okay, so that's 2 times and then divided by n minus 1. So that means the variance the same dimension. We can see we calculate the square of that for the same dimension. Okay, same dimension, both are the x. But if we want to find out that is how the one dimension is varied with another dimension, on that case we need to find out the covariance instead of just the variance. So that means standard deviation and variance can only operate on one dimension, but in case of the covariance it measures how much two dimensions vary from the mean with respect to each other. Okay, so that means if we consider if we have two dimensions, then if we want to find out that is how much one variable, or we can say one feature, varies with respect to mean from the other feature. Okay, so that's the measurement is called the covariance measurement. So it is in case of the covariance measurement, here is also the same thing. That means we can say xi minus of x bar, like here. So here is the xi minus of x bar. Here is also the xi minus of x bar. But we can see now instead of xi minus x bar, here is yi minus of y bar. So that means this is another variable. If this variable, if we can consider about the age, and this one is maybe the BMI or something. Okay, so another variable is this. Okay, then we want to find out that is the covariance between age and BMI. So that means how the age varies from the mean with respect to another one, that is the BMI varies from the mean. So that means if we want to find out, you want to measure how much two dimensions vary from the mean with respect to each other, then you have to think about the covariance. Specifically, in our data sets, we have many features. Okay, that's why for each and every feature, how one feature, that means one dimension, varies with another dimensions with respect to another dimensions, we want to usually measure that. So that's why the covariance is necessary. As in the PCA, what we have to do, that is we have many features and we want to keep the variabilities of the whole data set even after the transformation. So that's why we need to study the variability, and that's our covariance is there. So one example is here the covariance. For the case of the covariance, like if we want to find out a data set, the covariance of a data set, let's say in our data set we have like the hours of a study and obtained marks. So we have collected data from, maybe you can say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 students. Okay, we have collected the data from 12 students where n equal 12. Okay, 12 students. And now we want to find out the covariance between these two variables. Okay, the one is hours of study and another one is marks. Then how can we determine that? So specifically for this, our equation will be so covariance of covariance of H and M. So we want to find out this covariance of H and M. Then it will be from I equal 1, from 1 to n. N in our case is 12. N is 12. And here is xi. So that means we can say xi is initially we can consider out the hi minus of the h bar. So h bar is the mean value of h, the mean value of hours of study. So mean value of hours of study. So these are the hours of study data we got. And then the total, if we sum up, the total is this. And then the average or mean, we have to divide it by 12. So it will be 13.8. 13.92. Okay, 13.92. So this is our H bar. So H bar equal 13.92. So if that one is 13.92, then again we can see we have another variable that is called our m. So m is here. So m minus of m bar. M bar is what? M bar is our mean value of obtained marks. So these are the obtained these are our marks, and then the mean will be the total summation. Total summation is 749 divided by 12. So this will be our m bar. M bar is 62.42. Okay, 62.42. So now we can see that is what we have to do. We have to subtract H bar and M bar from H and Mi respectively. Okay, so that means try to find out Hi minus of H bar first. So Hi minus of H bar. So Hi, the original value of hours of study, like in this case it is 9, minus of H bar. So 9 minus of H bar is what? 13.92. Okay, 13.92. Then we will get negative 4.92. Similarly, the next instance is 15. So 15 minus of 13.92. 15 minus of 13.92. It will give us 1.08. Okay. So in this way, we have to find out for each and every instances what's the difference from the mean. Okay. So there's the deviation from the mean. So those are the values for that. Now we have to think about our the next variable, marks. For obtained marks, the original value is 39, and what's our mean value? The mean value is 62.42. So that means 39 minus 62.42, 62.42. Okay, so on that case you will get negative 23.42. Similarly, the next one is 56. So 56 minus 62.42, 62.42. So what we will get? We will get next, there's negative 6.42. Okay. So negative 6.42. So that means we got the Hi minus of H bar. So these are the values for that. And Mi minus of M bar. So these are the values for that. Okay. Now we can see we have to multiply these two. So Hi minus of H bar and Mi minus of M bar. So in our equation, we have to multiply these two. Okay. Then if we want to multiply, so these two values, these two columns we have to multiply, that is minus 4.92 times negative 23.42, and we will get 115.23. Okay, 23. Then 1.08 times negative 6.42 will be negative 6.93. Okay, so in this way we will get the multiplicative values, that is the multiplication of two columns, Hi minus of H bar and Mi minus of M bar. Then the next here is the summation for all the instance, all the 12 instance. So we have to sum up all these 12 values. That means for each and every instance. So the summation is 1149.89. Okay, 1149.89. So then we have to divide it by n minus 1. Okay, n minus 1. So n is our 12, n minus 1 is 11. So if we divide it by 11, then we will get 104.54. So this is the covariance. Okay, this is the covariance between our H and M. The covariance represents something here. That is, this is the positive relation. That means it indicates both dimension increase together. Okay, both dimension. That is, if we increase the hours of study, then the marks will also increase. And if we got some negative value, it means the inverse relationship. That means it indicates one increase and another decrease. Then if we got some 0, then actually those dimensions are independent. Okay, so we know now how to find out the covariance between two variables or between two features. In our data set, specifically, we can say that we have maybe many features. Let's say consider our 3 features, X, Y, and G, 3 features. So what we have to do, we have to find out the covariance matrix. Okay, covariance matrix. So that means X, Y, G. So here we have to consider again the X, Y, and G. So if you want to compute the covariance matrix, then at first we need to compute the covariance of X and X. So here we will get that covariance of X and X. So covariance of X and X, X and X is the same variable. Actually, it will be the variance of X. Variance of X, because the same dimension, okay, variance of X. And then we have to find out the covariance of X and Y. So here is the covariance of X and Y. So that means we have to find out the covariance of X and Y using the same, like the same formula, okay. So the covariance of X and Y. And then we can see we will get also the covariance of X and G. So this case, we will get the covariance of X and G. And then next, here is the Y, so Y and X, so covariance of Y, X we will get here. And then Y and Y, so this is actually the variance of Y, so we will get here the variance of Y, okay, variance of Y. And then this is our covariance of Y and G, okay, Y and G. So 2 variables Y and G, we can determine the covariance of that. And then G, covariance of G and X, covariance of G and Y, and covariance of G and G. So that is our variance of G, okay. Variance of G. So we will get this matrix, okay. So another thing I need to mention here, the covariance of X and Y, it will be the same as the covariance of Y and X. So the order, it doesn't matter here because the variables, 2 variables. The covariance of X and Y, it will be the same as our, so covariance of X and Y equal is this covariance of Y and X. So it means if we know this value, if we want to know, if we know this value, then we can use that here. Similarly, covariance of G and X, it will be the same as our covariance of G and X. So covariance of X and G, it will be the same as covariance of G and X. Similarly, covariance of Y and G, this will be the same as covariance of G and Y. Okay, G and Y. It means that actually we need to compute just the, maybe we can say upper triangle, okay. So these triangular values of this matrix. Then that is the lower triangular values we will get automatically, okay. So that's our covariance matrix. So that means in case of our data set, we have 4 dimensions, then our covariance matrix will also be 4 by 4. Okay, 4 by 4. If we have like maybe 10,000 dimensions data set, that means 10,000 features we have, then the covariance matrix will be 10,000 times 10,000, okay. So that will be our covariance matrix. In another way, we can say that the covariance matrix from our data set will always be the square matrix, okay. So that means we will get the square matrix. The covariance matrix will be the square matrix if we compute from our data set. So do you have any question up to this slide?
Sir, so what's the difference between variance and standard deviation?
Yeah, that's a square of that, okay. So that the square of that is our so it's kind of the, we can see for the standard deviation, you will get some lower values, and but if we square it, then we will get the just the upper values, okay. Like square root is there, and the square root will reduce your the values of the dimensions. So that's why if we know the variance, you can determine the standard deviation, and if you know the standard deviation, then you can easily determine the variance also.
Okay, sir.
Okay. Okay. So next, we need to have some knowledge. We can say we need to specifically know how to calculate the eigenvectors and eigenvalues of a matrix. So this is from mathematics. I think everyone of us actually know how to calculate the eigenvector and eigenvalues. This is the from our mathematics or engineering mathematics. So here is just only we can maybe review that work. But one thing I need to mention here, that is, if you already know the procedure of finding out the eigenvector and eigenvalues, if that procedure is different from what I will discuss in this class, and just follow whatever you know, because finally we will actually find out the same. So usually the eigenvector is a characteristics vector of a square matrix. So that means if you want to find out the eigenvector and eigenvalue at first, you need to ensure that, okay, the matrix must be the square matrix, okay, must be the square matrix. So in our PCA, principal component analysis, specifically we need to find out the eigenvector and eigenvalues of our covariance matrix. And I have already mentioned that the covariance matrix, if we construct from any data set, it will be a square matrix anyhow. So that means we can calculate the eigenvector and eigenvalues of our matrix. So the square matrix, the eigenvector is a characteristics vector, and this vector doesn't change its direction under any associated linear transformation. It means that so that means if you have a matrix like A, okay, so this is the square matrix, you will get a V, that is the vector, eigenvector, and that vector, it will remain same in any associate linear transformation, okay. So that means this vector will remain same. So if we know a matrix, this A is a square matrix, then you will find out this V, okay, V, and this V will not change with any linear associate linear transformation, okay, linear transformation. So that's our definition of our eigenvector. So this V is a vector that is non-zero vector. Then it is an eigenvector of a square matrix A. So AV is a scalar multiple of V always, and condition is written like this way. Here lambda, this lambda is called the eigenvalues. So this is our eigenvalues. So eigenvalue, lambda is our eigenvalue, and V is our eigenvector. So there are some properties of eigenvector and eigenvalues also, like if we know that there is x bar, this one, x is our eigenvector, and then any scalar multiple of x bar is also eigenvector, okay. So that means, so now we can see, we know that this relationship, if x is our eigenvector, okay, so then this relation will hold. So then we can see if we multiply x by any scalar, like here the alpha, okay, so we multiply the x alpha, so we will get a and then alpha x, okay, a then alpha x, and then this is the scalar value, okay. So what we can do, we can move it outside of our matrix A. So that means we will get alpha ax. So alpha ax, this ax bar is what? Ax bar is lambda x bar. So here we can put this is lambda x bar. Here is the alpha. Now again, we can put this alpha inside also. Okay, so that means we can see here, we can move it inside. So now lambda x bar. So now we can see A, this one, that is alpha x bar, equivalent to lambda alpha x bar, okay, alpha x bar. So that means this alpha x bar, this is our vector. This is a vector. This vector can be the P. This is the P vector. So that means the P is alpha x. So we can write now A P equal lambda P, okay. So we can see actually the the P also holds the same relation. Okay, P also holds the same relation. So that means we can consider we can say that P is also our eigenvector. So that means if we can find out any eigenvector like x bar, so any scalar multiple of that, like 2 x bar is also the eigenvector. But we need to find out the base one, okay, that is the x bar. Then how to find out the eigenvector? We want to just review it. So let's say a matrix is given. So this is a matrix, okay? This is a matrix A, 7, 3, 3, minus 1, and we want to find out the eigenvector of it. Then how can we find out the eigenvector and eigenvalues of that? And for that, the first step is we have to multiply an n by n identity matrix by the scalar lambda, okay? So at first, we have to take n by n identity matrix. The n is the dimension of our matrix A, okay? Matrix A. So that means we have a matrix. This is the matrix, and dimension of this matrix is 2. Okay, so 2 by 2. So that means we have to take identity matrix of 2 by 2. So identity matrix, that means diagonal positions are just 1 and other positions are 0. So this is our identity matrix. This is our identity matrix of the same dimension of A. So that means this now what we have to do, we have to multiply this identity matrix by lambda, okay, by lambda. So here is we will get this lambda identity matrix. Actually, this one will be our lambda 0, because we have to multiply this by lambda and 0 lambda, okay. So we will get like this way, this matrix, okay. So this is our first step. The first step is multiply n by n identity matrix by a scalar lambda, okay. Then subtract the identity matrix multiple from the matrix A. Subtract this lambda I from A, okay. So that means we will get what? From A, we have to subtract lambda I. So we will get from here, that is, this is the 7, 3, and then 3 minus 1. From here, we need to subtract, that is lambda 0 and 0 lambda, okay. So what we will get, this is the same dimensional matrix, subtraction is easy. So 7 minus lambda, so what we will get, this is 7 minus lambda, and then 3 minus 0 is 3, okay. For second row, it is 3 minus 0, that is 3, and minus 1, and minus lambda, okay. So this will be our resultant matrix. So this, we will consider this one as our reference matrix. So we will utilize this matrix several times in our eigenvector and eigenvalue calculation, okay. 7 minus lambda 3, then 3, 1 minus lambda, okay. So that is subtract identity matrix multiple from the matrix. And then the third step is find the determinant of the matrix and differ, okay. So that means we have to find out the determinant of this matrix. So determinant of this matrix. So that means that determinant of our A minus lambda I. So what we will get, it will be so two-dimensional. That means it's easy to find out the determinant. So 7 minus lambda, here's minus 1 minus lambda. So that means it will be 7 minus lambda times minus 1 minus lambda minus of the reverse diagonal values. So here is a 3 and times 3. Okay, so we have to do the math here. Okay, math here to find out, and then finally we need to calculate. Okay, so we can see the determinant, and after that, if we multiply these two, then we will get this value minus 9. And so here is lambda square, and then 7 lambda, 1 lambda, 6 lambda, and then minus 9 minus 7 is 16. Okay, 16. Then we have to find out, this is the equation, the quadratic equation. We have to find out the value of lambda, okay. value of lambda. So for this quadratic equation, if you want to find out the root, then what we have to do, we have to just put this one equal 0. Okay, this one equal 0, and then find out the root, that is the lambda. Okay, so it will be, how can we find out the lambda? So you can apply the equation like negative b plus minus root over b square minus 4ac by 2a. I think many of you already know this equation, 2a. So this equation, or we can say, we can, if this is easier, so that means we can do some middle term factorization. Okay, so 16 is there, 8 times 2, so that means 8 minus 2 is 6. So we can do the middle term factorization. Lambda minus lambda square minus 8 lambda and plus of 2 lambda minus 16 equal 0. Okay, so if we do the math, then you will get this value. Okay, lambda equal 8 or lambda equal negative 2. So this lambda is our eigenvalue. So we already got the eigenvalues. So one of the eigenvalue is 8, another one is negative 2. So 8 and negative 2. So now what we have to do, for each and every eigenvalue, we have to find out the eigenvector. Okay, we have to find out the eigenvector. So how can we find out the eigenvector from the eigenvalue? So at first we need to consider, okay, let's say if we consider eigenvalue lambda equal 8. So here lambda equal 8, considering that, if we consider lambda equal 8, then what we have to do, we have to put the value of lambda in our reference matrix. Okay, so that means the matrix I have already mentioned here, this matrix. Okay, we will use this matrix several times, so that's why I have mentioned that. Okay, just put the value of lambda here in this reference matrix. Okay, so that means 7 minus lambda, so 7 minus 8 and 3 is there, and 3 minus 1 and minus lambda. Okay, so then we will get this matrix, this matrix. So this matrix, consider this matrix is B. Okay, so that this matrix is B, this matrix is B. So now another properties of our eigenvector is, so this B matrix, if we multiply with our eigenvector like this, then we will get the 0 vector. Okay, so 0 vector. So this is another properties of our eigenvector. So we want to utilize this property now. So now we can see this is the problem. So here is our B, the matrix, and then this is our X. Okay, so X is X vector X, and we can see this is actually our A is 2 by 2. So in our vector, eigenvector, we will get the 2 components. So that's why here is, we can say this vector is 2 components vectors. Okay, so X1 and X2, and equivalent to our 0 vector. Okay, 0 vector. Now from this that is the relation, we want to compute the values of x1 and x2. Okay, values of x1 and x2. So that's our intention here. That means how can we find out the values of x1 and x2? Sometimes usually what we do, that means this is an easy example. That's why we can easily find out the values of x1 and x2 specifically. If we can directly get the values, then it's fine. Otherwise, maybe otherwise we can try to find out the relation, and from the relation we will get the values of x1 and x2. Okay, so there are several ways to find out that. So to find out that, there are several mechanisms you can consider. We can transform this matrix to the row echelon form, and then after that maybe we can find out our values. Okay. So like now we want to transform this. This is our, if it is a larger problem, then it's better if you can transform this one into row echelon form. Okay, echelon form transformation. So here in echelon form, usually what we need to convert this matrix. I think most of you already know about it, because you know how to compute the rank of a matrix. Then the same way. Okay. So here, so this is the matrix. So here, that means that the echelon form will be, usually we need to find out, maybe this is the ABC. Original matrix is like A, B, C, then B, C, D, E, F, then G, H, I. Okay, let's say this is 3 by 3 matrix. So we want to convert this one echelon form. Then what usually we do, in case of the echelon form, the A is there, the first row, and then this value will be the, we will get some values here, but D and G, these values must be 0. Okay, so we have to convert those 0, and for that we need some transformation, some form of transformation. So that means D must be 0. So that means that maybe we will get the A prime here, some values, not the A, but here will be 0 and here will be 0 also. Okay. Similarly for the B, so the B value will also change in your transformation, and C value will also be changed. But here is the C. Okay, so that means C will be here. Then this H must be 0. Okay, so here this H must be 0. Then the C will change. Then the F. Okay, so F will also change, and this one we want to get 1 or 0. Okay, so 1 or 0 we want to get from here. Okay, so this is kind of the echelon form. Specifically, we want to transfer this one. We want to actually transform this one to an echelon form. So that's why here, what we can do, we want to get 0 here in this position. Okay, in this position, and for that, what we have to do, this is the row 1 of the matrix, and this is the row 2 of the matrix. Okay. Row 2 of the matrix. Then we have to apply some form of transformation. And for the transformation, if we want to get 0 here, we can multiply the row 1 by 3. Okay, so row 1, this one by 3. So if we multiply this one by 3, then what we will get? -1. So we will get -3 here. -3 here. And here is the 3 times 3 is 9. Okay, so we will get 9 there. Then -3, here is the 3. So if we just add these two and replace the row number 2 with that, then we will get 0. Okay, so that's why the transformation, it is mentioned about like this. So 3R1, that means row 1 we have to multiply by 3 and then add the row 2. Row 2, that means if we add -3 plus 3, so that means 0. And then change the row 2 here. Okay, change the row 2 here. So on that case, we will get the 0 in this position. Okay, and again, here is 9 plus 9, and here is the -9. So that means if we add this row also, sorry, this column's values also, then we will get the 0 also here. Okay, 0 here. So this transformation we can utilize, like we got the -1 and 3. So here is the 0, here is also 0. And then if we multiply our x1 and x2 equal, what we will get, the 0, 0. Okay. So now we can see from here, this is, if we multiply this two, so we'll get -1. So that means negative x1 plus of 3x2 will be 0. Okay, so this is the equation we will get from this multiplication. And another equation we can get from 0, 0, here is x1, x2. So that means we will get 0x1. So that means 0 plus 0x2 is also 0 equals 0. So that means in this equation, no information is there. So we have only this equation. That is x1 plus 3x2 equals 0. So from this equation, we can write this one as negative x1 equal negative x2. So it means x1 equal 3x2. So now from this relation between these two variables x1 and x2, we can find out our eigenvalue. So in this case, we can see there is if we consider x2 equal 1, then what will be the x1? X1 will be, so that means x1 will be on that case 3. X1 will be 3. So that means our eigenvector on that case, it will be x1 is 3 and x2 is 1. So 3, 1. 3, 1 will be the eigenvector for that. So here is this is 3, 1 is the eigenvector for the eigenvalue 8. So someone can say that, okay, instead of this, can I take the 2 x2 equal to? Yes, you can, but again, we can see on that case, x2 equal to for that case, we will get x1 equals 6. So that on that case, the vector will be 6 and 2. Okay, and then 6 and 2, this one we can represent as here is 2 and then 3 and 1. Okay, 3 and 1. So as we already know that is if this one is our eigenvector, and then any scalar multiple of that is also eigenvector. Okay, so this is the scalar. We just multiply this by 2. So this is the base one. Okay, so that's why we have taken this 3, 1 and eigenvalue equal 8. So that means for the eigenvalue 8, we already got the eigenvector 3, 1. So similarly, we have to calculate the eigenvector for lambda -2 also, lambda -2. So if we apply the similar method, then you will get the for eigenvalue -2, the eigenvector will be 3, -1. Okay, 3, -1. So I think that's all in our eigenvector and eigenvalue determination method. So as I already mentioned, that means this method, if this one is familiar to you, just go it, and if you know something else, that means some other procedures to find out eigenvector and eigenvalue, just try that one. You will get the same eigenvector and same eigenvalue. So now we are ready to discuss about the PCA, principal component analysis. Someone asking something, sir, do we do the eigenvectors for 3 by 3 matrix? Yes, you can. Yes, we can determine the eigenvector for eigenvector and eigenvalues for 3 by 3, 4 by 4 matrices. Is the process of finding determinant different? Yes. For this case, for the matrix will be 3 by 3, then the determinant finding out the determinant of that is a little bit different. I think, yeah, we know how to do those things, okay? Because for the 3 by 3 determinant, there are, so I think you know about how to calculate the inverse matrix also. In that case, we have to determine the determinant of the matrix A. So this is 3 by 3 matrix. Okay, then how can we compute the determinant of this matrix? There are several procedure. One of the easy procedure to me is this one. So this is the matrix A. So what we have to do, the copy just the first two here. Okay, 105216. Just copy it here, and then what we have to do. This is the diagonal one. Multiply this, then you will get 0. Then multiply this, you will get 50, and then multiply this, you will get 0. And then you have to think about the reverse diagonal. So first matrix is this one. Here is the values. Okay. Then the next one. So here is it. And the next one is. Okay. So here is the 0. Then what we have to do, we have to subtract the diagonal values, summation of our diagonal values, and minus the reverse diagonal values. Okay, so these are the diagonal, reverse diagonal. Then you will get the value of the determinant. So this is how we can calculate the determinant easily, whatever the dimension on that case. It can be 3 dimension, 4 dimension, 5 dimensions. Is it okay? Mr. Sakib? Okay. Now I think it's better if you can go back. So how to find out the PCA? The PCA. Now the PCA, the principal component analysis. The step 1 is at first you need to have some data. The principal component analysis is unsupervised method. So that means if you have the data, if you have the class levels there, you have to drop the class levels column. Okay, class level feature. So PCA is unsupervised. So that means we have to drop the last column. Okay, that is our, not the last column, that is class level column. Then the next is subtract the mean. Okay, so we have to subtract the mean subtraction. At first, for each and every features, we have to subtract the mean from it. Subtract the mean. And then third step is calculate the covariance matrix. So we know that if we have 3 features, then we will get the 3 by 3, 4 features, 4 by 4 covariance matrix. Then step 4 is to calculate eigenvectors and eigenvector values of the covariance matrix. So we have the covariance matrix. We can find out the eigenvectors and eigenvalues of the covariance matrix as we already discussed. And then step 5 is choose the component and forming the feature vector. Okay, so that, and the next we have to form the feature vectors, and from the feature vectors we will select the components. Okay, select the components. So then how usually we do that? So let's say we have the data set, a small data set, just 2-dimensional data set. Okay, the X we have and Y we have. So that means 2 dimensions we have, X and Y. So like the same, that is, you can see this is age and BMI. 2-dimensional data set. Or you can say the same, we have also another example we already have done today, that is the hours of a study is H and the obtained marks is M. Okay, so what we have to do at first, we need to subtract the mean. Okay, mean subtraction. Subtract the mean. So here is the mean subtraction. That means we have to find out the X bar and we have to find out the Y bar. And from each and every value, we have to subtract this X bar and Y bar. So that means after subtraction of X bar, so this one actually the X minus of X bar, this one will be Y minus of Y bar. So these values we will get. So this is called adjusted data. Okay, adjusted. So and data. So adjusted data. So data. This is the data set. After mean subtraction, we have the adjusted data. The variable we can name it just data adjust. So now we can see that is we have 2 features, X and Y. So we can now find out the covariance matrix. So covariance matrix will be in this form. Okay, so this is X and this is Y. Here is the X and here is the Y. So the covariance matrix will be the X and X for this data set, you will get the covariance matrix. XX is this value and XY is this value. So XX is the variance of X. Okay, so the variance of X is this, and this is the XY, and then this is YY. So variance of Y. Okay, variance of Y, and this one will be the YX. The YX will be the same as XY. So that means this value we need to copy to here. Okay, so 0.65615 here is also 0.615. So this is our covariance matrix. We have already we know that how to compute the covariance matrix. So this is the equation we have already discussed about regarding this covariance matrix. Okay, we will get the covariance, and then the next thing is after getting the covariance, what we have to do, we have to covariance matrix. After we have to determine the eigenvalues and eigenvectors for that. So this is the covariance matrix. Now we have to determine the eigenvalues and eigenvectors. So I think we know how to calculate that. Okay, so just follow the steps I have already discussed here. Okay, so follow these steps: eigenvalues and eigenvectors. And by an identity matrix, subtract the identity matrix, find the determinant, solve this equation, and then find out the vector for each lambda. Okay, so we will get the eigenvectors and eigenvalues for that. And for this one, we have calculated the eigenvectors, eigenvalues first. The eigenvalues, this one is our lambda 1, and this one is our lambda 2. So this is lambda 1 and lambda 2. Okay, so eigenvector 1 and eigenvector 2. And for lambda 1, we will get the eigenvector. So this is our eigenvector for our lambda 1. So that means we can say this is our V1. And this is the eigenvector we will get for our lambda 2. So we can consider this one is our V2, eigenvector V2. So now the next thing is we have to form the feature vector. Okay, form the feature vector. So how can we form the feature vector? So feature vector. In the feature vector, we will place the eigenvectors, but we have to sort the eigenvectors based on the ascending order values of eigenvalues. The ascending order, that means we have to, at first we need to sort the eigenvalues in ascending order. So that means which one is largest here? That in this case we can see this one is largest. So that means lambda 2 will be placed here. Lambda 2 is greater than lambda 1. So in our eigenvector, that means feature vector, we have to place the eigenvector of largest eigenvalue first. So that means the V2, we have to place here V2, the first position, and then V1. Okay, V2 and V1. So this will be our feature vector. The feature vector will be this one. So that means in feature vector, this vector value, this value will be placed at first position, and then this value will be placed in second position. Okay, so that is our feature vector. So here is our feature vectors. Okay, eigenvectors. Then from here, the feature vector we have to develop in this way. Okay, so in this way. So that means this one and that one like this way. Okay, so that means we have to maintain this feature vector. So now in our feature vector we got this. So what we have to do now, we have to do some form of transformation utilizing our feature vectors. So the feature vector here, this is our feature vector. This is our feature vector. Feature vector. We have to transpose it. Transpose the feature vector. That's the row feature vector. Okay. So feature vector we need to transpose. That means if we can say that our feature vector we have F, then we have to transport it, that feature vectors, and then we have to multiply this one with the data adjusted, the adjusted data the variable name is data adjust. Then we have to transpose this one also, data adjust. Then we have to multiply these two to get our that is components. Okay, so component vector, or we can say, okay, final data. It is mentioned about final data. Final data. Okay, so in our case, there is f, the feature vector f. Here is the feature vector f. What will be the dimension of this feature vector? You can see this one we need to place first, and this one we need to place next. The dimension is still, it will be 2 by 2. So it will be 2 by 2. Then how about the adjusted data? So data adjust, what's the dimension of that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 10 rows and 2 columns. So feature vector is 2 by 2 and data adjust is 10 by 2. So if we transpose this feature vector, if we transpose it, here again we will get 2 by 2. Okay, 2 by 2 transpose. The row will be column, columns will be row. So that we, again the feature vector will be 2 by 2 after transposing. So if we transpose the data adjust, so originally data adjust is 10 by 2. If we transpose it, then it will be 2 by 10. 2 by 10. So we can see this is 2 by 2 and this is 2 by 10. So if we multiply these two, what we will get? 2 by 10. Okay, so that means here is 2, here is 2. We can multiply because this is the number of columns equal this number of rows. So we can multiply these two matrix, but the resultant matrix dimension will be 2 by 10. Okay, the dimension of the resultant matrix, it will be 2 by 10. So here is the 2 and 10, 2 by 10. Resultant matrix dimension. This is the dimension of final data. Okay, 2 by 10. So final data is 2 by. So here is the final data. It will be, the dimension will be 2 by 10. Now what we have to do, we have to transpose the final data. Okay, we have to transpose the final data. Transpose the final data to get the principal components. The PC, that is principal components, we have to transpose the final data. Then what we will get? We will get again 10 by 2, 10 rows and 2 columns. 10 rows and 2 columns. So that means this transformation, after this transformation, you will get this transform data. Okay. So this is transform data. This is called the principal components. So the first one is our first principal component. The second one is our second principal component. This is called the PC component 1. This is the PC component 2. In this way, we will get PC component 3, 4, 5 if we have the higher data dimensions. Okay. The PC component 1, it will hold the most variability of our data, and then PC component 2, it will hold the less variability than the first one, that is principal component 1, but it will hold the more variabilities than other principal components. As we have just only 2 principal components here, then the PC component will hold the most variability, and PC component 2 will hold the less variability than the principal component 1. So what usually we do, maybe if we want to just drop, then we need to drop PC2 here. So from 2-dimensional data, you want to make the 1-dimensional. So you want to reduce the dimension. So on that case, PC component 2 you can reduce and PC component 1 you have to take for maybe modeling the data. So similarly, if you have the 1000 dimensional data, then it will convert, maybe you can say there is 1000, the principal component 1 to principal component 2. In this way, maybe principal component 1000, oh, sorry, 10,000. But the principal component 1 will hold the most variability. So maybe you can consider just only principal component 1 and 2, so these two, and drop all other dimensions. So data will reduce from the 10,000 dimension to just only 2 dimensions, okay, 2 dimensions. So specifically, then how many principal components we need to select? How many principal components we need to select? It will be depend on, that is, how many, how much variability you want to hold in principal components. Okay, so the percentage of that. If you think about this one, that is our this one. Okay, the principal component 1, PC1 and PC2. How much variability will hold by principal component 1? So on that case, we can see principal component 1 will hold. The principal component 1 is actually from lambda 2, okay, lambda 2, okay, because we have already, we can say, sort. So principal component 1 from the lambda 2, that means this is the eigenvalue for that. So it will be 1.284 divided by 1.284 plus 0.049. So this much variability will hold by principal component 1, and for the principal component 2, it will be 0.049 divided by 1.284 plus 0.049. Okay, so if we can calculate, is 1.284 plus 0.049. So it is 1.333. So 1.284, 1.333. So this is, so here 1.284. So 96.33. Okay, so that means in percentage we can see this will hold 96.33% of the variabilities. It will hold by the principal component 1, and for principal component 2 it will hold the variability, that is from the 100 we can subtract this one, so it will be 3.77. Okay. So that means only 3% variability will hold by PC3, and PC1 will hold 96% of the variability. So that means if you can say that, okay, you want to hold 95% of your variability after principal component transformation. Then on that case, we can see just principal component 1 is enough for that. Okay, because this one has 96%. Okay, so on that case, it will select just only one component, principal component 1 will be selected. But if someone say that, okay, I want to hold 98% of the variability. So on that case, it will take the principal component 1. So the principal component 1 is 96.33. Then that's not enough, okay? Because 98, we have to make 98. Then we have to take the principal component 2. Then it will add another 3.77. Then this is 100% of the variability. Okay, so that means on that case we have to select 2 principal components other than just 1. So what usually it will do, that means your data, original data may be scattered in many ways, like this way. So the principal component it will actually transform your data in such a way so that maybe you will get the data in this components, okay, in this way. So we can see the data will be transformed in such a way so that maybe it will follow the PC trends. So this is the principal component 1. So we can see that most of the data points will be closer to this one, and then this will be the principal component 2. Okay, this is PC2. This will be the PC2. So this is our PC2, principal component 2. Okay, so in this way we can find out the principal components. One thing is we can go back to the original data from the principal components also by using this transformation. But actually we never go back, because it can be using the mathematically we can go back, but the procedure is this. Okay, the procedure is this. Okay, that's our principal component analysis. So that means from our any maybe data set, what we have to do at first, we have to subtract the mean and then calculate the covariance matrix for different features, and then we have to calculate the eigenvectors. Then we have to form the feature vector, and then we have to transform, and after the transformation we need to choose the components. Okay, so based on the variability we can select maybe the number of principal components necessary to hold those variabilities. So any question from your side? Do you have any question? If not, then I think we can move on to our next topic. Okay, then next, our LDA. The linear discriminant analysis. LDA. This is actually also from our PCA. Okay, this is the PCA, but we have extra things we have to do here. Okay. So in case of the LDA, linear discriminant analysis, finding the component axis in case of PCA that maximizes the variance of our data. Okay, so that means in case of the PCA, if the PCA component holds the variances in different dimensions. Okay, so not only the variances it will hold in case of the LDA, the another thing is it will also use another that is the properties that it will try to maximize the separation between multiple classes. So here you can see it will try to maximize the separation between multiple classes. So multiple classes, that means it will use the class levels now. So the PCA, this one actually I have already mentioned, this one is our unsupervised approach, but in case of the LDA, it will use the class levels. So that means this is supervised. Okay, so that means the class levels will be required for the LDA. So now, how can we find out how can we utilize the LDA for data dimension reduction? There are several discussions on it, but I think it's better if we can go directly to our procedure to finding out the LDA. So in case of our LDA, that is linear discriminant analysis, it has 5 steps. The first step is compute the d-dimensional mean vectors for different classes from the dataset. So that means we can see the class levels are there. So if you have the dataset and your dataset has 3 classes, then you have to compute the mean vector for each and every classes. Okay, so that means we can say there is the mean vector. Okay, the mean vector, mean value, mean 1, mean 2, and mean 3. So that means considering 3 classes. Okay, considering 3 classes. The mean vector for class 1, mean vector for class 2, mean vector for class 3. But now we can think about, like, for each and every mean vector, we have to think about, like, the number of features also, the dimension. Okay, so this is called the dimension. It is number of features. Let's say we have 4 dimensions. So this one is our one feature 1, and second feature is feature 2, feature number 3, and feature number 4. So we have 4 features. So that means for the first feature, the mean value for our class level 1. For this, the second feature's mean value of class level 1. Third feature's mean value of class level 1. And fourth feature's mean value of class level 1. Similarly, first feature's mean value of class level 2. Second feature's mean value of class level 2. Third features mean value of class level 2, fourth features mean value of class level 2, and first features mean value of class level 3, and all these are from class level 3. Okay, so we will get this type. So D dimensions. D means the number of features we have. So this is our D. This is our D dimensions. Okay, D dimensions. The next is compute the scatter matrix. So a scatter matrix is our variability matrix, okay, or variance matrix. So we have to calculate 2 types of scatter matrix. One is called between class scatter matrix, and within class scatter matrix. within class scatter matrix. That means between class and within class. So between class means if we consider class level 1 and 2, class level 1 and 2. So this is between class scatter matrix. And then we have to think about within class scatter matrix also. That is, within the class, the data has some variability, and that variability usually we call it within class scatter matrix. We will see how to compute that. Okay, the between class and within class. Then we have to compute the eigenvectors and eigenvalues again for the scatter matrix. Eigenvalues and eigenvectors for the scatter matrix. Specifically, we have two types of scatter matrix. Then the two types of scatter matrix we have to multiply. That means specifically not the multiply. One is inverse and another one will be there. So we will see it. And then we have to compute the eigenvectors and eigenvalues of those between class and within class matrices. And again, the next thing, will be the same like the PCA. That is, sort the eigenvectors by decrease in eigenvalues and choose k eigenvectors with the largest eigenvalues from dk dimensional matrix W. Okay, so that means we have to compute the eigenvectors and eigenvalues, and then we have to form the W, the eigenvalues and eigenvectors, and from that we will select the k times d dimensional matrix W. Okay, so that means instead of d times n, we need to select maybe d times k. Okay, so d times k dimensional matrix. So this one will be d times k dimensional matrix. So from the n dimensional vector, we will select just only the k dimensional. So that is our reduced dimensional. Okay, and use this eigenvector to finally get the value utilizing this. This is our x original, and this is our W. That is our after removing the unnecessary dimensions, we will get the k, and that is our W. So if we multiply these two, then we will finally get the y, and this y will be our LDA components. Okay, LDA components matrix. So this is how we have to calculate the LDA. And now let's do it with an example. So like consider that we have three classes of iris dataset. We know many of you already know about this dataset. This is also one of the popular dataset to explain machine learning. So let's say three classes data we have. The iris dataset, iris setosa, iris virgicolor, and iris virginica. Okay, so let's say each class have total 50 instances. So iris setosa we have 15 instances, iris virgicolor we have 15 instances, and iris virginica also have 15 instances. So that means this is the kind of the balance data set of three different classes, and total number of instances here is 150. Okay, 150. And we have four features for iris dataset: is sepal length, sepal width, petal length, and petal width. So four features we have. So here is this. This is the flower. One of the iris flower is this one. So this is our petal, and this is our sepal. And the length here is, we can see the petal length and petal width. So this is the petal length and petal width, and this is the sepal length and sepal width. Okay. And now, based on these sepal length, sepal width, petal and petal width, we want to find out the different types of iris flower. So there are three types of iris setosa, iris virgicolor, and virginica. So we have total 150 samples, and out of 150, 50 is setosa, 50 is virgicolor, and 50 is virginica. Okay. Now the data set, you can say that maybe the data set is like this. Some of the instances, okay, some of the instances we have total 150. So you can see this is the sample number 145, sample number 146, sample number 147, 148, and 149, and sepal length, sepal width, petal length, and petal width, and also the class level are given here. Class level are given here. Iris virginica, virginica, all these are from the virginica. Okay, the virginica. So that means the virginica we can consider these are the class number 3. All these are class number 3. So in X, if we consider X is our data set, we have total 150 instances, 150 instances from instance number 1 to 150. Here is the sample 145, 149. Okay, so this is the sample number 1, sample number 2, sample number 150. Okay, and this is for the sepal length. Okay, sepal length, and this is second features, sepal width, and this is third feature, petal length and petal width. Okay, and these are the class levels. Class levels. That is Y is our class levels. In this class, we have total 1, 2, or 3. Okay, so 1, 2, or 3 classes. Some are setosa, some are virginica, some are versicolor also. Okay, for this one, this sample, this is setosa. Okay, setosa means 1. The encoded value. Okay, so this is 1. The virginica, the encoded value is 3. So that's our Y. And we have the X. This is our X of dimension 150 and 4. So 150 and 4. Okay. So D here is our 4. 154. And for each and every class, we have 50. There is N, we have 50. Okay. Now compute the D-dimensional mean vector. So mean vector, we can see we have to compute the D-dimensional mean vector for each and every class. Okay. So that is the M1. We have to compute the M1. So M1, it will consist of so the mean value for sepal width, mean value for sepal length, sepal width, petal length, and petal width. So we will get the vector like this. Okay. So the M1. So this is the vector M1, the mean vector of class 1. The first value is 5.006. Okay. So for 3 classes, so that means similarly, this is the M2. This is the M2, and this is the M3. Okay, we got those M1, M2, and M3. Now the second step here. Okay, compute three-dimensional mean vectors for different classes. That means 3 classes we have. So we got M1, M2, and M3. Compute the scatter matrix. Okay, between class and within class scatter matrix. So now we have to compute the scatter matrix. To compute the scatter matrices, at first the within class scatter matrix, within class. That means within our data points of different classes. So within class scatter matrix, this is our SW, and then we have how many classes we have? Total C number of classes. Okay, so C here is in our case 3 is 3. So it means we will get S1, S2, S3. So S1 for class number 1, the data points we have to find out the variability on it. So to find out that, here is this SI. Let's say this is, we want to compute the S1. Okay, and for that specifically we have to do this. Okay, we have to do this. X minus of mi and x minus of mi transpose. Okay, x minus of mi and x minus of mi transpose. Or we can say that the summation of the multiplication of x minus of mi and x minus of mi. Okay, so we have already discussed this one, how to compute the variance and covariance. Okay, so if you can see here, the covariance specifically, this is hi minus of h and mi minus of m. But if we consider about the same variable, hi minus of h and hi minus of m h bar. Then here is this. That means if we multiply these two and then find out the summation, then we will get this value. Okay, get this value. So instead of that, we can do this, just the transpose of it. Okay, just the transpose of it, and we have already determined the mi using this equation here. We have already got the mi. Okay, mi. So mi we have already got this one. So that means we can see that x, this x minus of mi for class level 1. So that means class level 1, the class level 1, CLASS, for class 1, we want to find out the SI. And for that case, the x, this will consist only the DI, that means the data of class level 1. So we will get what? We will get the data set, the data values of just class level 1. So data values of class level 1, like from 150, we will get just only the 50 with class level 1. Maybe you can say the with class level Setosa. If we consider that from 1 to 50, from x1 to x50, all these are from maybe Setosa. These are Setosa. Okay, all these are Setosa. Then we have to subtract. That means we can see that the data we will get from the 4 dimensions. Okay, 4 dimensions, and we have to subtract each dimension. So on that case, maybe you can say this is our 4-dimensional mean. So we have 50. We have 15 instances. Okay, 15 instances. So that means for our that is our, we have total 15 instances, and we have 4 dimension. Okay, 4 dimension. So on that case, we can see this is the 4 dimension we have, and 50 values. From the 50 values, we have to subtract what? We have to subtract the mi for each and every dimension, for each and every dimension. So that means we can say this, if we consider our the x is for x1, like this is x1, this value, from this value, from x1 of sepal length. Okay, sepal length, we have to subtract the mean of that. So mean is our m1. So mean is our m1 for class level 1. Okay, for class level 1. Similarly, we have to think about our that is the x. So this is sepal length. Okay, so then x2 sorry, x2 of sepal length. So again, this is a sepal length divided that is minus our m1 mean for the first dimension. So in this way, maybe we can think about like x 50. Okay, x50 of sepal length and minus of m1. So we will get we will get total the 50 here. Okay, so this is m1. Then similarly, we have to subtract like x sepal length minus m2. Okay, not the sepal length, like this one is sepal width, m2, x2 and then sepal width minus m2. Okay, so in this way up to 50, and then third one will be our petal length, and fourth one will be the petal width, and then we will get this matrix. Okay, so this matrix, that means 4 50 this matrix. And then if we just transpose this one, so, okay, transpose this one, then we will get what? 50 times 4. If we transpose it, we will get 50 times 4. Then if we multiply these two, 4 times 50 and 50 times 4, we can see this one is the same. So number of columns equal number of rows. So we can multiply these two, and then we will get the output here is 4 times 4. Okay, 4 times 4, we will get the output here. We can see within class scatter matrix here. Okay, within class scatter matrix 1 2 3 4 1 2 3 4. Okay, 4 4. So this is the within class scatter matrix we have to compute utilizing this equation, or maybe using our just the summation. Now this is within class scatter matrix. The next thing is we have to compute the between class scatter matrix. Okay, between class scatter matrix using this equation. So in this equation we can see this is mi. We have already know the mi. So these are the mi. So m1, this is our m1, and then the m is our mean value for considering the whole data set. Okay, mean value for considering that. This is the m is our overall mean. Okay, the overall mean, and this is mi, and the ni, the sample mean, sorry, the ni, the size of the respective class. Ni is the size of the respective class for all the 3 classes. But we know that the iris data set, we considered the size of the each and every class is 50. Okay, so we have considered that means for class number 1 is 50, class number 2 is 50, class number 3 is also 50. But usually that's not the ideal case. So that means maybe we can some other data set if you utilize, then class number 1 maybe 30, class number 2 will be 100. Okay, so that's why the ni is there. This is called the size of the respective classes. And then mi minus of m, and here is mi minus of m. If we transpose it and then multiply this one, then we will get the between class scatter matrix. So between class scatter matrix we will get. So after getting the between class scatter matrix, will be this one. We will get the between class scatter matrix. So that means we have already got within class scatter matrix, and also we got the between class scatter matrix. And now we have to find out this. Okay, so what we have to do, we have to multiply these two. One is within class and another is between class scatter matrix. So within class scatter matrix, we have to inverse this matrix and then multiply this with the SB. Okay, with the SB, that is between class. And if we find out this, then multiply these two, then we will get A. Okay, so within class and between class. Why actually we are doing this? There is an explanation for that. I will explain it later. So here is the A, then we will get A here. Okay, A. This matrix A. So what we have to do, we have to find out the eigenvector and eigenvalues of this matrix A. Matrix A. Okay, so now what we have done here, that means, okay, we have already computed the within class and between class and inverse, and then here is the eigenvector for that. Okay, so eigenvector 1, eigenvector 2, eigenvector 3, and eigenvector 4 we have. So we have the 4 by 4 matrices. Okay, so that's why we have 4 eigenvectors here, 4 eigenvectors. But what we have to do next, that is we have to sort the eigenvectors based on the eigenvalues, again in descending order. Okay, descending order. That means the highest eigenvalue, we have 4 eigenvalues. The highest one is this one. These are the 4 values we have. Okay, so this is our lambda 1. So you can say the lambda 1 is 3.32 e to the power 01. Okay, so that means it is actually 32.3. Okay, so this is our lambda 1. And then this is our lambda 2. This is a 2.7 e to the power negative 01. So that means this is 0.27. For 3, this is negative 17. Okay, so that means the negative 0. Then we can say many zeros, 70 zeros, and then 0.2. And this one is again negative 17. Okay, so that means 0.000 in this way, 17 0 and then 2. Okay, so there is a 4.0, nearly the same. Okay, so that means we can see these are the values for that. So the highest eigenvalue is this one, and the next one is this, and those are nearly 0. Okay, those are nearly 0. So after sorting these eigenvalues, what we have to do, we have to compute the W. We have to compute the W. So usually we have to select the k eigenvectors, out of all the eigenvectors. So according to the descending order values of our eigenvalues. So that means the eigenvector generated from this eigenvalue, we have to take it. So we can see eigenvector, this is the eigenvector, that is eigenvector 1 generated from our eigenvalue, this one. And then this one is next. Okay, this one is next. So eigenvector, this one is next, eigenvector 2. So actually this one is here. We have taken these two. In most of the case, the value of the k will be c minus 1. C minus 1. C is number of classes. Okay, number of classes. In our case, Virginica, Vargicolor, and Setosa, so total 3 class. Okay, 3 class. So 3 minus 1, the k will be 2. So that means we need just only 2 LDA dimension. LD dimension. Okay, LD1 and LD2. 2 LD dimensions. So we will select 2 LD dimensions. Here is this, the first LD. This is second LD. So like the PCA, this PC component here, this is called the LD component. This is LD1, this is LD2. But PC is selected based on the variability score. Okay, that is summation of the variability. There is a threshold greater than that. But for LDA, the K is selected based on the number of classes, usually C minus 1. Okay, so that means we have selected the W here. Then utilize this W. You can say this is the W we have. So in this case, W is our 4 times 2. Okay, 4 times 2. So this one is 4 times 2 dimensional. Okay. So X is our n times 4 dimensional. We will get the Y. Okay, we will get the Y. So n in our case for iris data set, n is our 150 total. Okay. 150. So 154, and here the 4 times 2. So finally we will get what? We will get n times. So n times k. So here is the n times k dimensional. It means finally we will get 150 times 2 dimensional matrix as our data set. So this is how we can compute the LDA. Okay, LDA. This is, we can see LD1 and LD2 in our iris data set. Okay, iris data set. So this is just one class. This is another class, and this is another class. So we can now easily plot our data set. And instead of 4 dimension, we can see just only utilizing LD1, LD2, we can plot this. So Now, one thing I need to maybe discuss about how to compute the inverse. I think we know those one from our engineering mathematics course. So if we consider this is our the matrix, then here is one thing you have to find out the inverse matrix. Okay, it's W inverse matrix of W. So how to compute the inverse? So inverse is a matrix is 1 by determinant, and then here is the n. Okay, then how to compute the determinant of A? I have already discussed about it. Okay, that is so this is how we can compute the A, and then we have to compute the n. So n is our, we can see this is our A. Okay, so this is our A matrix A. And how can we find out the n matrix, the component matrix here? At first, this is 1. We have to take the 1, and then we will get this is small matrix. Okay, 1, 5, and 6, 0. Here is the 1, 5, and 6, 0. Then we have to consider 2. So here is the 2. If we consider 2, then remove the row and columns of the 2, then we will get here 0, 5, and 5, and 0. So 0, 5, 5, 0. And then 3, next we have to consider 3, then 0, 1, and 5, 6. Here is 0, 1, and 5, 6. And then we have to consider 0 here, then 0, this row and this column we have to omit it. Then we will get 2, 3, and 6, 0. Okay, 2, 3, and 6, 0. In this way, we have to find out all the component matrix. Okay, and then from each and every one, okay, from each and every one, we can see this. This is actually, we can say the diagonal values. 1 times 0 is our 0, and then minus 5 times 6 is our 30. Okay, 30. So this is the determinant of our the submatrix here. Okay, so that is our 0 minus 30 is, this is minus 30. This is minus 30. Similarly, here is our 0, and then minus 5 times 5 is 25. So here is negative 25. This is negative 25. Okay, and then the next one is 0 minus 5. So here is minus 5. In this way, we have to find out the determinant of each and every submatrix. And now we know that the sign, we have to consider the signs for determining the n. Then the first we have to start with plus, then next one is negative, and then positive, and then from the plus, then next one negative, then positive. Okay, in this way. So plus, minus, plus, and minus, plus, minus, plus, minus, plus, like this way. Okay, and then we have to now compute these values. Plus and minus is minus, so minus 30. Here is the minus 30. Okay, so the negative and negative is positive, so positive 25. Okay, positive 25. Then positive and negative 5, so here is the negative 5. And negative negative 18, so here is the negative 18. And positive negative is 15, so here is the 15. Negative negative is plus, so that means here is the 4. Plus 7, minus 5, and plus 1. Okay, so that means these are the values of n now. Now what we have to do, as we need to compute the inverse, so here is this dimension, that means we can set the diagonal positions. After fixing those, that means we have to keep this one fixed, the diagonals, and then we have to extend the upper triangular values with the lower triangular values. Okay, so that means the position here, this position, we have to replace with another position. So that means we have to extend the values of these two. That means 18 will be here and 25 will be there. So here is 18 and 25. And then this value, okay, this value and that value we have to extend. So here is the negative 5 and here is the 7. So negative 5 we have to place here and 7 we have to. And then this value and that value we have to exchange. So that means negative 5 here is 4 and 4 will be there. So this one will be our n. Okay, So now we can see, considering this one n and our determinant, that means determinant of A is 5. So what we will get, the inverse of A is this, okay? So that means this is our n and this is 1 by 5. So the inverse will be this. So this is how we have to compute the inverse of a matrix. So that means this is inverse matrix. Then we will get a matrix, and then the SB we have already got the SB. Then if we multiply these two, then we will get A. Okay, so from A we have to calculate the eigenvector and eigenvalues. I think this is all in our today's lecture. Then how to compute the LDA and PCA. Any questions from your side?
স্যার আমাদের ফাইনালের মার্কস ডিস্ট্রিবিউশনটা কেমন হবে? থিওরি কত মার্কস?
এটা বলা যায় না যে আসলে থিওরি কত মার্কস আমাদের 40-60 হতে পারে নিয়ারলি।
স্যার থিওরি কি হচ্ছে প্রুফ টাইপ হবে নাকি ডেফিনিশন টাইপ?
প্রুফ টাইপ হওয়ার সম্ভাবনা বেশি। ডেফিনেশন আসলে আমার মনে হয় না দেওয়াই ভালো ডেফিনেশন টাইপ। Okay, thanks all of you for attending this session, and that's all in our today's lecture. Thank you.
স্যার ফাইনালের কোশ্চেনটা স্যার বেশি ব্রড করেন না, মিডের কোশ্চেনটা বড় ছিল।
ঠিক আছে, ব্রড না হলেও একটু ট্রিকি হবে হয়তো। হ্যাঁ,
টাইম কনজিউমিং হয়ে যায় অনেক। থ্যাংক ইউ স্যার।
ওকে, থ্যাংক ইউ। মুতাসিম।
আসসালামু আলাইকুম স্যার।
ওয়ালাইকুম আসসালাম।
স্যার নন লিনিয়ার এসভিএম এ কি স্যার প্র্যাকটিস শিট কি দেওয়া যায় স্যার? অথবা স্যার কোনো রেকর্ডেড লেকচার কি আছে স্যার? কারণ স্যার স্লাইডের অঙ্কগুলো আসলে স্যার মানে খুব হয়ে যায় স্যার করতে গিয়ে।
অঙ্কগুলা
একটু টাফ হয়ে যায় স্যার স্লাইড থেকে অঙ্ক বুঝতে গিয়ে স্যার। যেমন স্যার আজকে স্যার লিনিয়ার এসভিএম এর অঙ্ক স্যার ইয়া থেকে করছিলাম, অ্যাকচুয়ালি স্লাইড থেকে করছিলাম আর কি। একটু মানে ম্যাপ করতে অসুবিধা হয়ে যায় স্যার, কোঅর্ডিনেট করতে অসুবিধা হয়ে যায়।
আচ্ছা ঠিক আছে, আমি একটা আপডেট করে দিই আর কি।
থ্যাংক ইউ স্যার।
ওকে, থ্যাংক ইউ। তালুকদার,
স্যার আমাদের এমএল অপস এর ইনভিটেশনটা কি আপনি পাঠাবেন নাকি আমাদের কোনো ফর্মে আমাদের ক্রেডেনশিয়াল সাবমিট করা লাগবে?
অলরেডি সাবমিট করে যারা অলরেডি করেছে আর কি প্রিভিয়াস ইনভাইটেশনের জন্য, তাদের তো আমি ডিরেক্টলি ইনভাইটেশন পাঠাই দিব আর কি। হ্যাঁ
স্যার আমি কোনো ফর্ম সাবমিট করেছিলাম না, আপনি
হ্যাঁ,
অটোমেটিক্যালি আমাকে
সেজন্যই যারা করে নাই তাদেরকে ফর্মে সাবমিট করতে বলতেছি আর কি। আমাদের এই ফর্মটা অনেক আগে দেয়া আর কি, নিচে এই ফর্মটা। না, এটা তো না, ঠিক না? ওকে, বুঝতে পারছি। এটা হচ্ছে আপনাদের ইয়ার থেকে নিছিলাম আমি সরাসরি, রেজিস্ট্রেশন শিট থেকে। হ্যাঁ, তাহলে একটা ফর্ম দিলে বেটার হয়, ঠিক না?
জি স্যার ওটাই
আচ্ছা, ঠিক
বলছি।
আছে। হ্যাঁ হ্যাঁ, ওকে, ঠিক আছে, আমি একটা ফর্ম দিয়ে দিব, তাহলে বেটার হবে। আচ্ছা, তার আগে আমি আজকে এটা আপলোড করে দিই। ওকে, থ্যাংক ইউ ভেরি মাচ। Where is the records?